This is it. So if it weren't for this question right here, I probably would not be standing in front of you and I would not be teaching today. So this is the question that I failed in that one, remember that video, the how to get a job at Google thing where I talked about failing an interview? This is the question where I stood at the board, I stared at it, and I started drawing boxes, just black boxes. I had no idea how to answer it. I had no idea how to approach it. I'd never done linked list problems. If it weren't for this question, like I said, I probably would not be teaching in front of you today. All right, so our interviewer gives us a question. They say, we have a linked list. So we have a linked list, and it's a standard linked list. You see, node, we have a next pointer. We have a node, we have a next pointer, we have a node, we have its next pointer. Every node has a next pointer, but it not only has a next pointer, it has a random pointer. And so these red arrows signify a random pointer. So this first node is pointing to the second node. It's just random. This second node is pointing all the way to the last node. And the third node in the list is pointing all the way to the first node. So the thing is, this complicates things because making a deep copy of a linked list with just next pointers, that's trivial. That's pretty simple. We just make a clone. We're advancing on the original list and we just clone each node. But with these random pointers, what we have to do is we're going to have to connect the clones. We're going to have to connect the clones and their random pointers into the same random assortment. So that presents us a difficulty. That is the roadblock my brain hit. I could not even recognize that roadblock. So the key is we find our roadblocks first. We have a linked list problem. Normally linked list problems are going to run in linear time and constant space. So that's going to be the case for this problem. The best solution is in linear time and in constant space. We're going to look at all of those solutions for this problem today. So before I even start with the actual question and going into the solutions, I want us to first hit the mental barrier. I want us to find where our mind gets stuck in this question and use what we know to try to clone this list and see what happens. Alright, so whenever we traverse a linked list or any singly linked list, doubly linked list, it's all about pointers. It's all about using pointers and advancing them as we do copies. So let's set a pointer on the first item. So now we have a pointer on the first item, and let's make a copy of it. Okay, so that makes sense. So we can't really do a copy of the random pointer because we don't even have that node yet in our clone list. So now let's advance our next pointer and let's just continue copying. Let's see where this takes us. Okay, and now we're looking at this node, and now we're going to copy this node. So let's make a copy, and however we implement this, it would be pretty straightforward. We would connect these two nodes, and now this is where we hit a mental barrier. This is what happened. In my interview, I knew that I needed to do pointers. Okay, I know how to work with singly linked lists, but I hit a mental barrier. Wait, when do I connect these random pointers? How do I get from my original list to my clone? Do you see how I'm starting to cook up problems? Do you see how I'm starting to think, wait, how is this going to be wired? Okay, I may be able to clone the list and give it next pointers, but that's not what this problem is about. These random pointers give me trouble. Getting to this mapping in constant time is giving me trouble. Do you see these thoughts? These are the key things you need to vocalize. These are the key things you need to watch. You need to watch these things and see them because they will help you get to the answer. So the thing is with these questions, there's what we already know and the connections we can draw. So we already know how to do normal iteration with a linked list, but I would have to say that if you've done enough problems and enough practice, you might already know how to clone a graph by this point. So if you can clone a graph, do you remember back to how we did that? We want constant time access into these clones to do a mapping, and it makes the mapping much easier to do. So what data structure does that make me think of? What solution strategy do I remember? Well, I could use a hash table. I can use a hash table to have access to this clone list so that, one, I can make these mappings, I can have constant time access to these mappings from an original node to a clone, and then, not only that, I can reach this node, and then I can set the random pointer of the clone node by reaching to the random pointer of the original node, and then I can reach its clone in constant time. So that is the utility of a hash table, and that is how we're going to have a linear space solution. So let's walk through the linear space solution. As always, code is in the description. I would read the code first or watch this first. It's however you learn, but we have the code. So let's walk through the linear space solution. All right, so now let's look at the linear space solution. Both the optimal solutions are going to be linear in time. We're going to have to touch every node in the original list, we're going to have to expand linear time in order to make a deep copy. But where we can optimize is space. So we're going to do linear space because we're going to hold a linear amount of mappings. When this list gets arbitrarily large, our mapping amount is going to scale in a linear fashion. So what we're going to do is we're going to do two passes. On our first pass, we're going to create every mapping. I will connect nothing. No connections will happen. And on the second pass, when all my nodes exist and all my clone mappings exist, I will be able to iterate over the original list and I can snatch the clones through the hash map. The hash map lets me snatch the clones. So let's go through this and you'll see what I mean. So now we're going to put an iteration pointer on the first node. Okay, so an iteration pointer is on the first node. Let's make a copy of it. And remember, this is a hash table mapping. We have mapped the original node to its clone. So we're going to be able to reach right in and do any operations we need on the new list being built. This is the utility of a hash table. So we can advance our pointer and now we can make a copy of that node. We've advanced the pointer again and now we make a copy of this node. And now let's advance it again, and now let's make a copy of this node. So what is going on, here's our original list, it's wired up in memory. Here's our new list, and we have all of these nodes just sitting dead in the water in memory, unconnected, no pointers connecting them in memory, and that is where these nodes are sitting. This is our first pass's job. What our hash table does is, when I have a reference to this node, constant time access into its clone. When I have a reference to this node, constant time access into its clone. That is what our hash table does. Its mapping allows us to execute rewirings very efficiently. So now what we do is we do a second pass. I'll put my iteration pointer on the head. Okay, so I'm pointing here. My job at each of these nodes is to populate the next field and the random field. So what we need to do is, how do I populate this clone's next field? Remember, our hash table is giving us access to this clone. So this node, we're going to have to say, this node's clone, hash table, give me the clone. Okay, I have the clone now. This clone's value, .next, is going to be this node. How do we get to this node? cur.next in the clone map, and then we're going to wire those together. Again, code is in the description. I look at the code first before you hear me say it in words, because it's easier to understand the words once you see the code. It's more structured. So now what we're going to do is do that wiring. And so now we need to wire the random pointer. So we see that the original random pointer does this, right? So what I say is, go through the clone mapping, I'm at this guy. I want to set as random. So I'm right here, and now what I need to do is I need to go original cur node dot random. I'm over here. What do? I hop to its clone, this node's clone, right here. And now I have reference here, now I have reference here, and I connect them. This is it. This is our algorithm. We're going to do this for every single node. And remember, our mapping is giving us this utility. It is giving us this constant time access. I'm going to keep saying it into its clone. If we have reference here, we have reference here in constant time. So now let's advance our pointer and move forward in the list. And so now we're pointing to the next node in the original list. So again, jump down to the clone, we have reference to that. And then jump to the random in the original list, and then we have access to this clone. And now we can wire these guys together. And then again, we would do the next wiring. And now we can advance the pointer to the next node. I'm sorry, this is kind of getting sloppy, but you should get the idea. So now we want to wire the next. Again, hop down into the clone. And then what we do is go next and hop down to this clone. And now we can connect these. All right, and now we can do the random connection. We go to this node, we hop down, we have this clone. And now we go to its random, which is over here, and then we have this clone. So now we can connect this guy to this guy. And then finally we advance to the final node. And then what we do is we copy its next, which is just null, and it has no random value, so we wouldn't even copy that random value. So this is how we take a deep copy of a linked list with random pointers. It's all about making the mapping first, making all of these nodes, and then executing the connection of pointers in our clone list because we have access to our clones from each of the original nodes. And when you do that, it's very simple. The linear space solution is very straightforward. So we can get a little tricky. we can improve our space complexity. This is probably not going to be something you're going to execute in an interview, but I want to show you it just so that you are aware of this and that most of these problems have optimal solutions that are kind of out of reach sometimes in the time of an interview, but are still interesting to know because it could express some extra degree of problem-solving ability, but to be honest, it's still kind of up in the air. So if you're uncomfortable with linked list problems, definitely check the code in the description. The constant space approach will definitely take you for a ride and you are going to get confused very quickly, but give it time, read the code over several times, and you will eventually just understand it. You're going to see it's just rewiring things. We just need to keep track of how we're rewiring pointers. It is nothing more than that. We're going to spend linear time and do constant space. So now, remember, this is going to be linear in time because we're going to expand linear time going through the original list, and linear in space because we're going to be storing n mappings. We're going to store a mapping to each node's clone. This is not including the output, which is going to be O of n because we're going to have a linear amount of clones. But what we can do is we can improve the space. We can improve the space to constant space. So I want to show you that approach as well, and I definitely, again, want to warn you, it's going to be tricky. Okay, so now we're going to look at the constant space solution, and we're going to see how we're going to do this. So we're going to set a pointer on the first node of the original lists, and let's see where this takes us. I'm going to create a copy node in memory. Let's do that right now. And remember, at all times, I want you to think of mental barriers. When we use constant space, what is the mental barrier that I face? Well, if I'm using constant space, I can't keep mappings. I can't have a hash map to map to this clone. How am I going to get access to the clone? And it's a little trick that we use. What we do is we utilize the next field on the original node to map to its clone. So we bridge the gap like this. Do you see how I just pointed the original node's next field to its clone? And now, what we're going to do is, we're going to point the next field of the clone node to the next node of the original node. So let's do that. And remember how I said this is all about rewiring. This is where things get tricky. I need you to stay with me. So all we did was, we pointed the next field of the original node to the mirror node, and we pointed the mirror node to the original node's next node. The thing is, we need to restore the original linked list. The reason we do this is because we're going to need to restore these pointers. We need the original node to point to its clone. But what we do is, we cannot screw up the random pointer, and we need to restore the next field at the end. So what we do is, we remember the original node's next node on this mirror node. So again, read the code and follow this description, but again, this is tricky at first, take your time, but it will make sense. So now we're going to go to the next node, and again, this is still our first pass. And what we're going to do is we're going to point the original node's next to its clone, and then we're going to point this next value to the original node's next. And now we're going to advance our iteration, and then we're going to create a clone and rewire this next to that clone. And what we're going to do is we're going to point the copy nodes next to the original nodes next. And then we'll advance our iteration, and then we're going to create a clone, and now we need to adjust the next to point to the clone, and now we need to get the clone to point to the original nodes next, which is just null. So this is our first pass. So what did we just do? What we just did is we created a clone mapping, and now we have not used any additional space, but now we have access from the original node to the clone node. So now we have to do a second pass. So now the second pass's job is to do what we were doing before. We want to fill in the random pointers. And now what I'm going to do is I'm going to set an iteration pointer at the first node. And now what I'm going to do is I'm going to reach to cur.next. That is my clone. Cur.next.random, I want to set that. I want to set the random pointer for this node. What do I set this random pointer to for this node? I go cur.random.next. What is that? The clone of the original node's random. So now I have this node, I have this node, and now what can I do? I can set the random mapping. Do you see? Mapping. We can set the mapping. So that is how we do it. Let's set it. And again, this is probably going to get sloppy, so definitely check the code out, but I still want to do this walkthrough. So now what we just did is we did our job. And how do we get to the next? Do you see how we destroyed the original node's next value by mapping to its clone? How do we get to the next value? Well, I can go cur.next next. That was the point. That's why we did that. That is why we stashed the next value of the clone as the next value of the original, so we can go cur.next, and now we're at the next point in our iteration. Let's do it. Now we're right here, and we do the same thing. Cur.next is right here, and cur.random.next is right here. Connect them. Okay, and now what we can do is we can advance cur.next. And now what we can do is cur.next, we're right here. And now we can go cur.random.next, we're here. So connect these guys. And now we can go cur.next, get to him. Now we have the last node, and now we can set the random value. There's no random value to set, so now we can advance, and then we hit null, and we're done with our second pass. So guess what? Our clone is fine. Our second list is finished. But do you see a problem here? Do you see how we messed up the next node to create a mapping to save space, to keep ourselves constant space? The thing is, we can't just screw up the original caller's list. We have to restore their list. So what we need to do is we need to go back and do a third pass. The first pass's job was to create the mapping to our clones. The second pass's job was to fulfill the random pointers, and the third pass's job is going to be to restore the original list and then reap the final list. So what we need to do is restore the original list. But the thing is, this is pretty straightforward, because remember, we have access to the next node of each of these original nodes. All we need to do is go cur.next, and then the next value of the clone is the next value of the original, because we stashed that. So why don't we just restore that? Again, the code is in the description, and it's fairly straightforward to do the restoration. And so after our final pass, we're going to rewire each of those nodes to the original next, and we're going to rewire each of these new nodes to their next nodes, which we're going to have access. Remember, we can go cur.next to get the clone, so the next of him is going to be this guy's next value. That is how we do this problem in constant space. So would we have to do this in an interview? Probably not. But I wanted to show you it and give you a code sample in the description just so you are aware of it. So this is this problem. This is the problem that took me down, and eventually I learned it, and I think you can learn it too if you take the time to read these problems over, realize that most of these problems are linear time and constant space, and all about rewiring and working with pointers. The more you do, the better you get. It is that straightforward. So that is all for this video. If you like this video, hit the like button, subscribe to the channel. This channel is about empowering software engineers to excel in the interview and do their best. So that is all for this video, and we